Welcome back, ladies and gentlemen, to another video with Mr. Kenton. We're continuing our discussion and our notes on topic 1.5, which goes through atomic structure and electron configuration. And the previous video we watched on topic 1.5 really focused in on that electron configuration piece. And so now there's one more component that I want to add to this, which focuses in on Coulombs Law. Now, as we begin to talk about Coulombs Law, I do want us to just talk about, just very briefly, the difference between inner electrons versus outer electrons within an atom. Now, our inner electrons are going to be also referred to as our core electrons. And so these are going to be everything but the valence electrons. And if you've forgotten what a valence electron is an electron that's in the highest occupied energy level for that particular atom. So if you're thinking back to electron configurations, if you're thinking about that principal quantum number, the number that comes before the S, P, D, or F designation, that's going to be that energy level that it corresponds to. So the electrons that are in that highest energy level are going to be the valence electrons. Everything else are going to be those core or inner electrons. Now, the outer electrons, like we said, also those valence electrons, these are going to be the electrons that for us as chemists we're most interested in, because those electrons are the ones that take part in chemical bonding. Now, when you start to think about this, just a quick question here, and as you're looking at this video, feel free to pause it, work out this problem, come up with your answer, and then, if you have a question about that, feel free to ask me. But how many core electrons does silicon have? How many valence electrons does silicon have? I think it would be a good exercise for you guys to go through to write out the electron configuration of silicon and then distinguish which of those electrons are core electrons or inner electrons, and which of those electrons are valence electrons or outer electrons. So take some time, pause the video, go work on those problems, and then come back so that we can finish it out by talking about Coulombs Law. Now, hopefully you paused the video, hopefully you were able to work through the silicon problem and figure out the number of core versus valence electrons. Now, Coulombs Law is this last piece that I want to tie into electron configuration. And so as you can see, we've got this formula here. We've got Fe, which is our electric force, is going to be equal to Ke, that's our constant here, the Coulomb constant, times Q1 times Q2, where Q1 and Q2 are the charges of our object, and then over R squared, where R is our distance between the two particles that we're studying. Now, Coulomb's law is extremely important because it's going to give us understanding of how charged particles interact with each other based on their proximity. Coulomb's law is going to be something that is going to be extremely important as we begin to look at periodic trends. You might remember from Honors Chem, you talked about periodic trends, but you probably didn't get a good explanation as to why the trends behave the way they do. Well, Coulomb's law is going to be a key piece for us to understand the periodic trends. Now, what Coulomb's law is communicating, right, is that based on the charges of these particles, it's going to tell us whether or not they're going to be attracted to each other or whether or not they're going to repel each other. And like it states here, Coulomb's law quantifies the amount of electrostatic force that two charged objects exert on each other, which causes either an attraction or a repulsion between them. Now, if you're looking at the formula, that means if you have two particles that have the same charge, that means they're going to repel each other. So their overall value, the Fe, the electric force, is going to have a positive value. But if they're oppositely charged, then what that's going to do is, if you had that negative number, if you're looking at the magnitude of the value, the fact that it's negative is going to indicate that there is an attraction, so those two objects are going to move closer together. Now, taking a look at what those variables compose of within that, so Fe is an electric force. Forces are going to be measured in newtons. So Fe is always going to be measured in newtons. Ke, it's our constant, and you notice its units are newtons times a meter squared per c squared. That c squared is a coulomb. It's a unit of measurement for charge. Now Q1 and Q2 in these cases, they're the charge of the object, so those charges need to be given in coulombs. And then our radius, the distance between the charges, those are going to typically be measured in meters. And if you look at how that plugs into the equation, if you have two charges on the top, that would give you c squared. If you've got r squared on the bottom, that would give you distance squared. So then you would just be simply left with newtons after multiplying by the constant. Okay. So again, Coulomb's law is going to communicate that obviously the closer the objects are to each other, the greater force they're going to exert on one another. The farther apart they are, the less attractive force they're going to apply on each other. Now, some qualitative applications of Coulomb's law. So getting into those periodic trends, this first thing here, ionization energy. If you recall, ionization energy is the energy required to remove an electron from an atom or an ion. Now, so the energy required to remove an electron from an atom or an ion. Now, obviously, as you begin to remove more and more electrons, it does become increasingly more difficult to remove those electrons. Well, Coulomb's law gives us an understanding of why those energies are the way they are and how that's playing out. The second qualitative application is with something that's called effective nuclear charge. Now, I imagine for many of you, effective nuclear charge is probably a new term that you're not familiar with. And so I want you to think of effective nuclear charge as the charge that the charge from the nucleus that pulls on the valence electrons. And so just think about it this way. The protons are residing in the nucleus, and they're positively charged, and you've got the electrons that are in the electron cloud. Now, positive and negative charges, when they get close to each other, they have an attractive force. And so that attractive force is going to be determined based on this effective nuclear charge, right? And so the effective nuclear charge takes into account the fact that those protons are pulling on the electrons in the electron cloud. Now, in addition, effective nuclear charge is going to take into account something that's called shielding. And shielding is just a fancy way to talk about how the electrons that are in the electron clouds are going to prevent one another from being attracted to the nucleus. The electrons that are part of the core electrons are actually going to shield and prevent the valence electrons from feeling the pull of the nucleus, because they're going to tend to repel, those core electrons are going to repel those valence electrons. Now, an overly simplified way to determine effective nuclear charge is to simply take the number of protons minus the shielding electrons. And shielding electrons is just another way to refer to the core or the inner electrons. Now, that is an extremely oversimplified way to calculate effective nuclear charge. In actuality, it's not so simple, but for where we are right now, that's a good enough way to get to it. Now, taking those two things that we're talking about, ionization energy and effective nuclear charge, we can begin to examine those things within the context of Coulomb's law. So the ionization energy for an atom or an ion can be estimated using Coulomb's law. And what we're going to do is we're just going to consider the size of the atom or the ion, which we have experimental data that we could use and look at to figure out what the sizes of an atom or an ion are. And we can take a look at the effective nuclear charge of that particular atom or ion. Now, the size of our atom is going to be the distance component within Coulomb's law. So that r squared piece, if you were to take into consideration the distance between two of the same atom, that's going to be your distance component. And then the effective nuclear charge is what we're going to use for our charge piece in that component. Now, as we look at those two things, a trend or a pattern that we should be able to predict is going to follow. If the atom is large or if the ion is large, when we're comparing it to another atom or ion of a similar charge, then it's going to have a weaker attractive force between its nucleus and its valence electrons. Or, if the substance is smaller, has a smaller effective nuclear charge, it's also going to have a weaker attractive force. That's going to be more prevalent when we're starting to move within a row on the periodic table, but the smaller the effective nuclear charge, the weaker the attractive force, right? That makes sense. If there's less pull of the nucleus, there's going to be less of an attractive force between the charged particles that are interacting. Now, where this gets, since we're only looking at this qualitatively, when you start to really dive into it, these two concepts, they can work against each other. And by these two factors, we're talking about the size and the effective nuclear charge. They can work against each other. But when we start to look at this, distance tends to be the determining factor. It's going to play a bigger role than the effective nuclear charge piece. Doesn't mean effective nuclear charge can't influence Coulomb's law, but the distance component is what's going to play the bigger role. Hope that makes sense. Now, some questions for us to consider as we think about Coulomb's law. If you were to look up the ionization energies of sodium to bromine, you would find that the ionization energy of bromine is significantly larger than that of sodium. And so then the question becomes, well, why is that the case? And really, in a sense, it's going to boil down to the fact that bromine has that greater effective nuclear charge, right? And so it's going to hold on much more tightly to its electrons than sodium will, and so it's going to be significantly more difficult to remove an electron from bromine as opposed to sodium. You know, we could also consider, how does the reactivity of alkaline earth metals, so our group 2 metals, change as we move down the group? And then we want to ask ourselves, well, why does this happen? Well, what we know from the trends is that as we go from the top to the bottom, that those alkaline metals, they get more reactive. They're getting larger. And so what's happening is, according to Coulomb's law, the nucleus has less of a hold on the valence electrons as we get further and further down the periodic table. So that means that those electrons are more easily to lose and to react chemically. And so that means the Coulombic forces of attraction are weaker as we move down that particular group, and therefore they're more reactive. Now, a question for you guys to consider on your own as I kind of close out this video, you know, you might be to consider, why are phosphorus and oxygen more likely to form covalent compounds with each other as opposed to ionic compounds? And think about how Coulomb's law might even play into that as well. Ladies and gentlemen, I do appreciate you joining in and finishing out topic 1.5 with me, which focused on atomic structure and electron configuration. And today's video just focused in on Coulomb's law. And so I look forward to seeing you guys again real soon. Take care.